All right, next up is the Robinson annulation. Annulation just means that we're going to form a new ring. And this really isn't a new reaction. It's just an application of our previous reactions. So what we're going to have is the first step is going to be a Michael addition. And then in the second step, we're just going to do an aldol reaction, addition and condensation. So let's go ahead and take a look at an example of this. This is a reaction that when you look at the starting materials and the products, it looks extremely complicated. So what you want to do is really just take it step by step. So in order to have a Michael addition, most times we're just going to want our doubly stabilized compound, right? That can doubly stabilize an anion. And then we're going to have our Michael acceptor, our alpha beta unsaturated carbonyl. And then we just add a base. In this case, we can add both of them at the same time because this proton right here is significantly more acidic than any other proton. So that's what's going to be deprotonated. All right, so that's the most acidic proton. And that's going to cause our compound to act as the nucleophile. And then this guy down here is going to be the electrophile. And so after that first step, after that Michael addition, our end product is going to look like this. And of course, this can look confusing, so make sure you're numbering your carbon. So for example, if we number this 1, 2, 3, 4, that carbon number 3 is going to be our nucleophile, and then it's going to attack our carbonyl. So I'm going to call this 5, 6, 7, 8. And so we're going to form a bond between C3 and C6. Or my bad, C8, my bad. This is going to turn into a negative charge, and then we're going to do our 1,4 addition, not the carbonyl, my bad. So C3, C8 bond formation. All right, we want to do the Michael addition. 1, 2, 3, 4, and then this will be 8, 7, 6, 5. So probably not the best numbering scheme, but you can use whatever numbering scheme you want as long as you get to the kind of right endpoint. And so after attacks, then it does the proton transfer and the tautomerization, and then this is our Michael product. So that's at the end of our first step. Next up, what we're going to do is an intramolecular aldol. And what we notice here is we have different places that we could form this aldol, but we have here is 1, 2, 3, 4, 5, 6. So we have a potential for a 6-membered ring. And remember that 6-membered rings are favored. So what we're going to have here is our base cause this carbon to become negative, and then an aldol reaction in here. So overall, this is an aldol addition with the C5 and C2 bond formation. And then I'm also going to sneak a proton transfer into here. So we've got our 6-membered ring, so we can just number it, or we can just draw a 6-membered ring, and then we can start numbering arbitrarily, 6, 7, 8, and then 3, 2, and 5, right? Why am I picking those numbers? Because these are the numbers that are within my ring. And then we can think about what we have on each member. On number 6, we're going to have our carbonyl. On number 2, we're going to have a methyl, and then an O-, which gets protonated into an OH. And then off of carbon number 3, we're going to have our ester. So that's our aldol addition. After this, we can do an aldol condensation. So we can have some base come in and essentially do an E2 elimination. to give us our final product, right? You can see how we formed a ring now, and this is an annulation reaction. Overall, I think it's pretty tricky to go from the reactants to the products. So in most cases, I'm going to give you both and then ask for the mechanism, but maybe I'll sneak in a couple other types of problems here and there.